All right, so let's do a little bit about simulating data in R. And the reason that we want to learn about how to simulate data in R, we've been doing this a little bit already. We want to be able to generate data, draw data from a population without specifying the entire population distribution, right? And so if instead what we can do is just specify the factors of the conditional and marginal factors that together make this joint distribution, we can draw data from it and kind of do our own experiments and play God. So let's imagine we have a scenario where we have we imagine we have a population of interest and we want to measure these different variables for people in that population. And the variables in this case are age, whether or not they're using a diuretic, which is a kind of medication that people get for many reasons, but in one reason if they have high blood pressure. We want to know what their history of blood pressure is, and we want to know also measure if they have a heart attack in the next 10 years. So maybe this kind of represents some observational study where we're interested in the effect of diuretic use, people taking this drug or not, if that affects whether or not they get heart attacks in the future, and whether or not those effects depend on how old they are or what their blood pressure actually is. So if we have that scenario, how might we start imagining building a distribution that could possibly represent these variables in this population? So you can start by building up a DAG. And usually the most intuitive way to do it is to decide for you. Again, we're playing God here, right? So this is all made up, but we can, it's a useful tool because you have to be able to think this way, like creatively, about the real world, to think what might be the relationships, what might be the distributions, right? So it helps to be kind of creative and play. So first step is to decide on what should depend on what. So you might imagine, okay, if I'm God, I might be first deciding what somebody's age is, and then based on what their age is, I decide what their blood pressure is, whether they're using diuretics, whether that could go into also how I decide whether they have a heart attack in the next 10 years. So let me just put in these arrows here. And then I go to the next node and I think, okay, well, blood pressure should also affect, it should also be part of my decision of how I assign somebody a heart attack, and also how I assign somebody diuretic use, because presumably doctors are looking at their blood pressure to determine whether they should get a diuretic or not. And then presumably whether they're getting this drug also determines the risk of heart attack. So that's it. That's my DAG. You can kind of organize this maybe if you like also in terms of time. That is also helpful, right? So the first thing that happens is somebody is a particular age. That age might, maybe this is kind of contemporary with whatever their blood pressure is at that age, but you could still imagine there's like some kind of dependence there. Or you would want age to be determining of blood pressure. You might think blood pressure and age determine diuretic use, and all these things go into heart attack. So by time ordering, I just mean that maybe diuretic use does not impact the prior blood pressure. So maybe these are variables that are measured at baseline. This is not something that's impacting prior blood pressure, nor is diuretic use impacting somebody's age. So this is just one way that you could kind of lay out a DAG for these variables. And again, the idea here is just imagine you're playing God, right? So this is one way that you could think about generating these variables. And I think it helps to be concrete. Also, you can put this into R. So how would you reflect this kind of DAG or data generating process in R? You have to decide on what the actual distributions of these things are. So let's start with age. All we have to do here is pick a marginal distribution for age, because there's no arrows going into it. So it's going to be a margin. This factor of the overall probability distribution is going to be a marginal factor. So let's start. Again, we're just making it up. So in this population of interest, I haven't told you what it is, but let's just imagine that age has a marginal distribution. It's a mean of 60 years old with standard deviation of 5 years. And next, let's decide on how blood pressure gets assigned to people in this population. And I've decided that it's going to be normally distributed, where the mean of the blood pressure depends on the age. So that is reflecting the fact that this age arrow is going into blood pressure. I could have the dependence could have been some other form. I could have said the standard deviation depends on age, and that would change what the joint distribution is. But the fact that this arrow is going in just means that age is going in here somewhere. And now let's decide on, oh, and by the way, I mean, the way I did this is reflective of the fact that people who are older have higher blood pressure. And the numbers that I chose here, 120 over 40 and 20 for the standard deviation, just kind of reflect normal values that I should be getting. Like if I put 60 in here, the value that I get out here should be like the average blood pressure for people who are 60, right? Roughly speaking. And this represents some kind of variation among people who are 60. What's the variation in their blood pressure generally? Now let's decide on how diuretic use gets assigned. So this is a binary variable. It's going to be 0 or 1. So I'm going to say I'm flipping a coin. For each person, I'm going to flip a coin. But the probability of heads or tails depends on their prior blood pressure and their age. And it depends on it like this. So I'm going to say if their blood pressure is greater than 140 and their age is greater than 40, then they're going to have a high chance of getting a diuretic. Why did I choose it like this? Because this reflects the fact that for people who are over a given age, if they have high blood pressure, doctors are probably going to prescribe them something. But if for young people who have high blood pressure, doctors might be more hesitant. They might think it's something that might resolve. I don't know. Don't quote me. I'm not a doctor. They might think that'll self-resolve, so they have less chance of actually intervening. Similarly, for older people who have low blood pressure, there's not much reason to intervene. And if somebody's young and has very low blood pressure, there's very little reason to intervene. But there's still some positive probability here. Why? Because, I don't know, diuretics are given for lots of reasons, not just for blood pressure. So this reflects that there's some other random stuff that's affecting whether or not somebody's getting diuretic use that doesn't have to do with what I've measured in this data set. And then lastly, let's decide on how heart attack gets assigned. Here I've said heart attack is also a coin flip, and the probability of getting heads is related to the age, blood pressure, and the drug. And so in this, I'll explain what this other junk is here, but right at this point, all you need to understand is that older people are positively affecting the risk. Well, I should say maybe negatively. Older people are more likely to get heart attacks. People with higher blood pressure are more likely to get heart attacks. But taking the drug, this minus sign is reducing the risk of getting a heart attack. And then this term out here is basically just saying, is establishing what the baseline risk is if all of these things took some kind of baseline values. So if I've come up with this code, I can now call it. I can draw 100 samples and get this data set, which is, again, totally fake, but I'm simulating sampling 100 people from some population that has this distribution. And this distribution is following the factorization given by this DAG. Okay, so I can look at this data set, and here's just some plot, making some plots. So I'm showing you here that, for example, if I'm looking at age and blood pressure, there's some correlation here. There's a difference in the blood pressure of people who are getting the drug versus not getting the drug. You can do all sorts of kind of sample statistics by looking at the data that you draw. So again, this is really nice. We'll use these kinds of things again and again later in the course to illustrate properties of our statistical methods. Because our statistical methods, I think we'll talk about this in a second, but our statistical methods are going to be stuff that takes data that looks like this, where we don't know. We don't have this code, right? We get this data from the real world, not from some code where we know what the DAG looked like, right? We get this stuff from the real world. And we want to infer something about the population, right, from just having this sample. By being able to do simulations like this, you can say, okay, if the distribution in my population looks something like this, right, what will the samples often look like? And therefore you can apply your method to samples drawn from that population and say, where you can actually kind of compute the right answer, where right, what this effect is or something like that. And then you can compare how your method is, whatever answer your method is giving you from this data set. You can repeatedly draw data sets, look at what your method is telling you compared to the truth, right? And say, hey, is this method actually good or bad? And we're going to get a lot more into that later in the course. But that's the core idea of being able to do simulations like this, and how having being able to think in terms of DAGs, helps you make these kinds of simulations. We'll also see that having this DAG is it tells you things about how your methods will perform. Because if you have a simulation where certain things are independent or are not if you have a situation where in the population certain variables do or don't follow certain independencies or conditional independencies, that will impact what it is possible to say from the data. So if you know more things about the DAG, you're sure that certain things are independent or aren't, that makes it easier to make inferences from the data. And if you don't know those things and you have to assume them, but you're not sure, that actually can make it impossible to do certain things, to say certain things, just given these data. So we'll get a lot more into that later in the course. For now, our purpose is just to understand how we can actually do these simulations and have some conceptual idea of why we're doing that. That will help us understand these things in the future. Okay. So I'm interested, let's look at this, in the relationship between HRT and stroke later on. I also want to consider age, because I know it's related to both. So what is a plausible DAG that you might draw to represent this relationship? So I might think, again, if I'm playing God, I might imagine that HRT will affect stroke. Probably not the other way, because this is something that's happening in the future, and this is something that's happening in the past. I also want to consider age. I think it's sensible to assume that age is affecting HRT. That is, first I could pick somebody's age. Depending on what age I get, that'll help me decide whether or not they're going to get HRT or not. And then similarly, age is telling me something about stroke. So this is interesting. Well, we'll get to this in a second. Let's consider now this thing down here. Let's say instead you have a situation where there's an experiment being run, and a coin is being flipped to determine who gets HRT. So let's draw the DAG to represent the relationship between HRT, stroke, and age within the context of this experiment. So here I have HRT, I have stroke, and we have age. And the difference now is that HRT is being determined by a coin flip. So what that tells you is that there's no arrows going into it. Well, I mean, if you had coin, right, that would go into it. But coin has no arrows going into it. So HRT has no arrows going into it. There's no reason anything else should change, though. So we still have a situation like this. So this is the key difference between a randomized study and a non-randomized study. We have a difference in the DAG. Something else I wanted to point out earlier is that this DAG is totally generic. Like if we just have X, Y, Z or something, right? All this is saying is that our distribution factorizes as Z given Y comma X, and then f of Y given X, and then f of X, right? So we know we could actually draw these arrows all pointing the other direction, because I could factorize this in a different way. It's not unique. So I could draw this a different way, and it could still represent the exact same joint distribution, even though I've chosen to draw it with the arrows going this way. I could draw it the other way, right? I could say, first, pick if somebody gets a stroke or not. Then use whether they got that stroke to infer whether or not they were on HRT. And then use whether or not they had a stroke and HRT to infer their age. And I can actually have some data generating distribution where the data coming out of this looks the same whether or not I do it that way or the other way. But here, I can't exactly do that. So here I just have f of, so let's call this one, again, Z and X and Y if I want to just abbreviate. Here, all I know is that we have this. And now I cannot, I can't put a new arrow here, or actually, I can't totally reverse these things either. I do not think that this entirely works to do it like this. So this is not exactly the same situation, because here, for example, I'll show you what I mean. So here, for example, I don't need to do it in the densities. I can just play the game. So this is the case that represents this randomized experiment. Okay. Here I can ask, are x and y independent marginally? And the answer is yes, because if I draw this path, it goes through stroke, which is a collider in this case. And now, so this DAG represents distributions where x is independent of y. However, if I were to draw the DAG like this, where the arrows are going the other way, x is no longer independent of y, because information can flow from z is not a collider. And so these two DAGs can't be equivalent, right? Whereas the DAGs up here, where I've changed the order of the arrows, actually are equivalent. Right now, that may not you may not see it totally like the relevance of that, but this is really fundamental about it's a fundamental difference between this situation up here, which represents an observational study where you're just going out and collecting data, right? And you're not really doing anything to intervene. And this situation here, where you actually have additional information because you intervene by flipping a coin to assign HRT, that tells you that for sure HRT is marginally independent of everything else that was existing at that time, like age, which tells you that this joint distribution, you can narrow things down a lot more, right? Because here you can't really tell the difference between this situation and this situation, whereas here these two things are different. So being in a randomized experiment, basically you're narrowing down the set of possible probability distributions between the variables, and we're going to see later that actually is super helpful, because you can actually infer, for example, whether or not HRT caused decreases in stroke, whereas here you can't say that for sure unless you want to make additional assumptions, which we'll talk about later.